Hi everybody, Ethan Atkins here, and today I'm going to talk about interesting mathematical formulas. There's a myriad of mathematical formulas that exist in the universe that have been brought into fruition, both naturally in the universe and both by human beings. But I'm just going to go over about 5 different formulas, specific formulas that I find that are the most crucial to development in the human race and our understanding of mathematics. And just overall, I find some of these equations, formulas really interesting for how important they are and our understanding of the universe we live in, and also the applications that they could have for making art, even weapons in some cases, and a multitude of other applications that these formulas can have. And also just sheer curiosity, just speculating on possibilities and infinite nature that mathematics presents to us. So the first one's probably one of the most well-known mathematical formulas on the planet. It's E equals mc squared, which is energy equals mass times speed of light squared. And speed of light can be converted into 3.00 times 10 to the 8th power meters per second. And this formula was created by no one else other than Albert Einstein, and it was created in relationship with his theory of special relativity. So what does E equals mc squared exactly mean, besides meaning energy equals mass times speed of light squared, meters per second? Well, basically, it expresses that mass and energy are essentially different forms of the same thing. Therefore, mass and energy are equivalent, equal. If mass is deviated from its original form with pressure or with a certain temperature, mass and energy can be used in the same way and therefore equal. Energy can become mass, and mass can become energy, and vice versa, right? So it's a very interesting equation that helps humans understand aspects of the relationship of stars and planets in our solar system, in our universe. Helps us understand the speed of light, why, the concept of redshift, for example. Why are certain galaxies billions of light years away while some are just simply millions or thousands of light years away? Well, this concept of the speed of light was popularized and made much more apparent by Albert Einstein. And it's a very interesting formula that is still being, it's still somewhat of a contentious formula today. This equation is much more contentious today because, it's still unexplored how this equation applies to smaller units of matter, such as quarks and subatomic particles. So many scientists have negated Einstein's theory of special relativity and E equals mc squared, because they believe it only applies to larger bodies of mass and energy, but it gets really murky, and it's still fairly nebulous and fairly, we're very unsure of quarks, how this in subatomic particles, how this applies to them, to electrons, to atoms, to smaller units of matter. And this equation also expresses that small amounts of matter can release enormous amounts of energy, such as a nuclear reaction. This formula helps kind of be an enzyme catalyst for nuclear fission. Ernest Walton was actually the first scientist to split the nucleus. He did so in the 1930s. He split the nucleus of a lithium atom. So around the 20th century, mid-20th century, all these extremely important discoveries were being made by scientists all over the planet. One of them decided that they could figure out how to, first of all, Ernest Rutherford was able to find electrons in the nucleus of an atom, while Ernest Walton was able to, split a nucleus of a lithium atom. And then you have Albert Einstein figuring out basically that energy, if it's small amounts of matter, can release large amounts of energy, and this can cause a nuclear explosion. As you can see up here on the right, it's been used for multiple applications involving mass and energy, such as satellite communication and power plants and nuclear fission. So there's a lot more to dive into this formula, but as of right now, that's the simplest summary I can give you for E equals mc squared. There's much more in-depth summaries of this formula, but it's an extremely fascinating formula equation, and I think it's just amazing that someone was able to bring into fruition this amazing concept of mass and energy being equivalent. So the second one is one everybody's familiar with, the Pythagorean Theorem, which is simply a squared plus b squared equals c squared. And this formula was created by the Greek philosopher Pythagoras thousands of years ago, created the Pythagorean Theorem. So this formula adheres towards the fundamentals of Euclidean geometry. I talk a lot about Euclidean geometry and propositions and postulates and common notions that allow the concept of one-dimensional, two-dimensional, three-dimensional shapes to be brought into fruition. And how if a right angle is equal to a right angle, they're equal if and the part is greater than the whole, and the ability to describe a circle. You have Euclid to thank for that aspect, but Pythagoras was able to bring in this concept of the right triangle, and he stated that the square of the hypotenuse, the squared, a squared, is equal to the sum of the square of the other two sides. That's what he called them. A lot of them we know them as the leg B, leg A, or in right triangles cases, adjacent and opposite legs. But basically, it simply states that the square of the hypotenuse is equal to the sum of the square of the other two sides of the triangle. So C squared is the hypotenuse, and A squared plus B squared equals the hypotenuse. I almost see it as if you were to take leg A and leg B and collapse them to make a 100-degree angle, it would equal the hypotenuse. It would be the same length. That's a way I like to visualize it. It's an extremely interesting concept that, and it's become an extremely fundamental part of geometry. Being able to prove this theorem. It's still geometry. It says geometry. Humanity has used this formula for ever since it was brought to fruition by Pythagoras. So it's a really essential formula for understanding the relationship of shapes, primarily right triangles, isosceles triangles, rhombuses, different sorts of triangles, and how the sum squared of two, the other two sides of a right triangle will equal the length of the hypotenuse. And as you can see on the right here, maybe probably zoom in a little bit. Might crush some words, but it's okay. It's okay. We already went through it. So you can see this is the Pythagorean equation. How basically using basic algebra, you can make the hypotenuse still equal by using different formulas. So c squared obviously equals a squared plus b squared, and then we have c squared equals square root. Just c equals the square root. So hypotenuse equals the square root of a squared plus b squared. So if you square this a squared plus b squared, it would still equal the hypotenuse. Then we use basic algebra by using if one of the legs, say adjacent or opposite, equals the hypotenuse squared minus one of the other sides squared, and that square root of that equals one of the sides of the triangle, right triangle, and b equals square root of c squared minus a squared. So they're all interchangeable. By using basic geometry and basic algebra, you can figure out that there's a lot of interchangeable formulas that you can use on top of the Pythagorean theorem, and that's called the Pythagorean Equations. And that's an extremely important part of geometry and basically our understanding of shapes. So I really enjoy looking at problems involving Pythagorean theorem and the Pythagorean equations. So that one's really interesting, and the fact that someone was able to come up with this equation in Greece thousands of years ago shows how advanced our civilization was even just thousands of years ago. So it's fascinating how far we've come as a civilization. This one's really interesting. There's really not much. There's not really an exact founder of this concept, but it brings in question the concept of infinity, and how there's this endless mystery of infinity, and involving mathematics and numbers. So this equation is 1 equals 0.9999999. As you can see right here, it's 0.9992 infinity. this equation expresses that 1 and 0.999 of infinity are essentially the same thing. Both sides of this equation are equally balanced. And the infinite repeating decimals of 0.9 is the smallest number possible, but not less than all decimal numbers, and it's only less than 1. And it brings into play really interesting concept of how far can a number go before it becomes greater than 1 again. So 0.9 is the closest we can get to being less than 1. So technically they're equal, because if this 9 continues to be infinite, but you don't add a 1 or another 9 and end it, it becomes 1. So therefore, it just goes on forever. It's technically, most people would agree that it's equivalent to 1. And that really is interesting, because it doesn't really, the only thing about this formula is it doesn't bring in other aspects of mathematics, such as negative and imaginary numbers. It doesn't bring in really complex numbers. It simply relies on the Archimedean property of the number lines of the lines. Of numbers on a line cannot be greater or less than numbers ahead. It's an interesting concept. How basically it relies off the concept of infinity. And what exactly is the Archimedean property? Let's look it up. What exactly is the Archimedean property? So it's an abstract algebra term. It's named after Greek mathematician Archimedes of Syracuse. It's a property that is held by only some algebraic structures. So that's what I mean. This only adheres to algebraic structures and decimals, but it doesn't really get into too much detail about negative numbers or complex and imaginary numbers. And it is a property of having no infinitely large or infinitely small elements. So there's no infinitely large or infinitely small elements, numbers, integers. So 0.99 to infinity brings into question endless mysteries of infinity. And so no infinitely large or small element can exist. This causes humanity to remain fascinated with the endless mysteries of the infinite, the infinite number of mathematics, and how mathematics can present to you numbers that are literally the best notation of infinity. 0.9 infinity is probably a great representation of what infinity could look like. So that's a very interesting formula. This one's really cool. I really enjoy this one. And after this one, I'll show you just a basic website you can go on to really interact with this concept, or just really look at how basically how polyhedrons are constructed. Like, polyhedrons to me are really fascinating. Shape, geometric shape. Dodecahedrons, tetrahedrons are really interesting concepts. And so this formula is really interesting, and it doesn't always work. That's the thing. It's not absolute. It only works for certain formulas, certain polyhedrons. So this formula, f plus v minus e equals 2, well, what does that mean? This formula was brought into fruition by Lenard and Euler, and this formula expresses that for all polyhedrons, so if it's a regular polyhedron, and the lines do not intersect within the polyhedron, if these units of measurement, so if units of measurement are plugged into this formula, the final answer will always be 2 for any polyhedron. Faces plus vertices minus, I think it's all the faces. Number of faces equals 2. So faces of the polyhedron plus vertices of the polyhedron minus the number of edges. No matter what kind of polyhedron it is, it will always equal 2. So that's a really fascinating concept to think of. And this is something you can look at that proves it. That proves that this is a formula that only adheres to polyhedrons, but it does not adhere to icosahedrons. Icosahedrons are much more complicated, and the only problem with them is that they have one less vertex compared to polyhedrons. So therefore, if you were to plug in this formula of v minus e plus f equals 2, in this situation, v plus v, f plus v minus e equals 1. So basically, every just because a icosahedron has one less vertex, it causes every time for it to be 1 instead of 2. And that's an interesting concept to think about. And also this equation can be interchangeable. The point is that it will always equal 2 for polyhedrons, or it will equal 1 for it will equal 1 for icosahedrons. So as you can see here, a tetrahedron has 4 faces, 4 vertices, 6 edges. So if you were to plug in this formula, V, so V, 4 minus 6, negative 2, plus 4, that equals 2. And it's just interesting how cube, same thing, 2. Octahedron, dodecahedron, the answer is all 2 for these. Icosahedron, 2. That doesn't seem right, because it wouldn't be 2. I don't know why it says 2 there, but it should be 1. For this case, it would be 1. Icosahedrons have 1 less vertex, so it would be 1. So that's really interesting. So the next one in the final formula I'll show. Well, actually, but before that, let me just show you this website. It's pretty interesting. It's called EulersFormula.com, or Euler's Formula on MathIsFun.com. And you can actually see these formulas, and you can look at a icosahedron and kind of mess around with it. You can drag it around. It's really fun and interactive to look at this geometric beauty. You can explode it. Isn't that pretty cool? You can actually see all the vertices and the faces in clear detail, and you can change how it looks. For example, you can change the way the colors are. You can make it just simply 2 different colors. To me, this is really cool. You can just do that in glass. It's pretty interesting. Look at that. Pretty interesting, right? There's some other colors. Pure glass. Then beams. Ooh. Crazy, right? Pretty interesting. So yeah, that's a cool website to look at if you're ever bored and want to mess around with a icosahedron or interactive polyhedron. It's fun to do that. So now let's talk about the last formula that I'm interested in. It's involving fractals, and I just did a video about fractals. So this concept is even more infinitely complex, but also extremely interesting. So I have a few different formulas here. So the first one is z equals z squared plus c. Well, what does that mean? Well, this formula was created by Benoit Mandelbrot. Mandelbrot, some people say. And this formula is the building block. It's the essential formula in order to create fractals, which fractals are like these things right here. These really interesting pieces of art. And the units are inputted. These are usually whole numbers between 1 and 2. And they're inputted in this formula, basic, positive, and negative integer iterations. And the concept of fractals is that it relies off iterations, it relies off an endless cycle, therefore making it infinite. And you'll see what I mean by infinite in a second. But this formula gives out a basic, almost like a Cartesian plane. It gives out a complex plane with horizontal and a vertical axis to be created using complex numbers multiplied by I. And this is where it gets interesting. This is where it stops to make sense for a lot of people. So what is I? How do you make a complex number I? That should be pretty interesting. Sorry, I was going to recall. But so this mix of iterations causes a fractal plane to exist, a complex plane, in which coordinates, which is z equals z squared plus c, these coordinates can be mapped out in order to position the fractal a certain way. And then when it comes down to colors of the fractal, that's decided by the computer and by other codes that people use on their computers. But it can also be completely arbitrary colors that is been inputted into the system, the computer, the CPU, the GPU. But the interesting thing is that a complex number is multiplied by I. So I is equivalent, is synonymous. It is the square root of -1. Well, the square root of -1 isn't a number. It's an imaginary number. And this is where it gets very interesting, because the fact that the square root of 1 is an imaginary number gives the ability for fractals to be infinite, because it continues that iteration of trying to calculate what is the square root of -1. And this mix of iterations of imaginary complex numbers and basic integers can be plotted as coordinates for positioning, size, shape, and color. of the infinite complexity and size of a Mandelbrot fractal set on a computer, creating beautiful fractals. As you can see right here, here's just simply the area. This is the formula for the area of a Mandelbrot fractal. So, yeah, so let's look at some photos. This is a pretty basic Mandelbrot, fractal. And it relies simply off plugging in these numbers into onto a blank canvas, or through coding on a computer. And as you can see, this is what it looks like on a computer when it's been inputted. The formulas have been inputted. And there's a really cool picture of a Julia set, which relies off Benoit Mandelbrot's formula, but also vice versa. They're inextricably linked, Julia sets and the Mandelbrot fractals. This is a really nice photo. This one's pretty cool. But yeah, so those are my favorite interesting and important mathematical formulas. Really quickly, play with this. I can show you an online fractal generator. This is just useful fulgs.net, and you can actually kind of play around with you can't play around with the values, but you can mess around with zooming in with it and deciding which kind of fractal set you want to be. So there's a quadratic Julia set, multi-Brot set, polynomial Julia set, rational map, Newtonian fractal, novas, phoenix fractals, burning ship fractal, and burning ship Julia set. So as you can see, they rely off these negative numbers and scales and render times, and these are all the numbers that are inputted. And what if I just zoom in? What if I just zoom in right here? It's pretty interesting. Right? Continue, and then I can reset it. What do I want? I want to put it over here. That'd be pretty cool. So it shows how mathematics is as idiosyncratic and esoteric of a field it can be. It can create very beautiful things. Not only will it help you understand equality between two legs of a triangle and its hypotenuse, it can also produce infinite amounts of art. And fractals are infinite; they just continue to go and go, multidimensional. And let's see, maybe let's get another one. So this is a multi-Brot set. So Julia sets are probably my favorites. This quadratic Julia set. So Julia sets are pretty cool. Look at this. I actually can mess around with this though. Let's see what happens. See, but just by changing one integer, completely changes what I'm staring at. So make it 3, or let's make it 8. Wow. Make it like an interesting number. Would be a cool number. 5, 3, 6. I don't know. Wow. Just by changing numbers, and make it something else that it wasn't previously. It's interesting. Whoa. Look at that. tricky, bro. What happens if I change one of the polynomial terms? What happens? Maybe -2? It looks like it changes the position. Maybe let's do 1? Make it 1. Wow, so it looks like changing the position. Let's make this 2. See what happens. Seems like somebody just changing it. 2, 2. Wow, look at that. It changed that right there. The middle, it almost looks like a chakra. That middle portion almost looks like a chakra, right? So you kind of see the similarity? Let's see, let's find a good example. Like that kind of looks like this. Different levels. So I can change the parameters on this one. Wow, isn't that crazy? Looks like some interdimensional being. I'll change it to 3. And this one 1. Rendering. Whoa! That's different. It takes a lot of time to render. My computer is getting destroyed right now. So anyway, that's pretty cool. So yeah, you can mess around with these websites yourself. I'll actually probably maybe I'll copy the links and put it in my video. But yeah, that's my video. I think mathematical formulas are interesting. Thanks for watching, everybody.